Welcome everyone. We are the Ionosphere-Thermosphere twin. Before we dive into the challenge, here are the researchers, Michael and me for the science side, and Linnea and Liz for the machine learning side, as well as the faculty and advisors whose efforts have made this project possible. Now, in the last decades, modern society has become increasingly dependent on complex technological infrastructures, both on the ground, in the air, and in space. Many of these systems, such as GPS, communication satellites, and power grids, are highly susceptible to disruptions caused by solar activity. These disruptions can pose serious risks to the reliability and safety of our systems. Let's look at a few relevant examples with Michael.
Thank you, Simone. The ionosphere has a major influence on the performance of GPS systems, so we're going to take a look at that. Our skill at forecasting ionospheric events must keep pace with the exponential growth of GPS-related devices everywhere in our lives. Reliability and high accuracy are required to support the growth of aviation, agriculture, construction, and transportation sectors. Currently, the agricultural sector shoulders $30 billion of losses due to GPS errors in planting, fertilization, and harvesting. And in the construction industry, mistakes must be torn down and rebuilt. GPS errors alone drive $88 billion of losses. But beyond financial losses, there is real, life-critical impact to society today. Dense, transatlantic routes are established to coordinate high-traffic demand. These routes depend on GPS accuracy in order to hold allowable safety margins, and an unexpected ionospheric event forces pilots to rely on their internal navigation systems. These systems cannot satisfy the required safety criteria for positional knowledge, presenting significant risk to pilots and passengers en route.
Thus, the final link that connects the Sun and our planet is the ionosphere, a region of the upper atmosphere extending from about 50 to thousands of kilometers in altitude, and is partially ionized by solar radiation. The dynamics of electrons in this region are influenced by various factors, including geographic location, solar wind, and geomagnetic activity, and can lead to phenomena called geomagnetic storms. One of the most informative and widely used observables of the ionosphere is the total electron content, which quantifies the total number of electrons along a vertical path from the ground upwards. Here we show a sequence of TSE maps generated by the Jet Propulsion Laboratory using a Sunlock reference frame. These maps serve as a foundation for building data-driven models of ionospheric behavior. Now, given how critical it is to predict the ionosphere's behavior in order to safeguard our system, we began our challenge with a simple but ambitious question. Can we forecast the total electron content?
Yes, with the support from Google Cloud Computing and machine learning, we did. So essentially, this is a big data problem. We're working with over a terabyte of data spanning many different sources, formats, and cadences. It was a crucial task to get all of these datasets cleaned, aligned, and ingestible by our model, be it for a forecasting, nowcasting, or classification task. And on top of that, we needed to be able to pick and choose which datasets we wanted to use to train our models in order to best determine which data streams are crucial for our problem. So towards this, we have developed an ML-ready data product that will be made available for the community to help accelerate future research in heliophysics. So now, given our data product, we needed the full ML pipeline to make use of it. In developing our framework, we've opted for a modular design. This allows us to easily switch between different ML models in the middle, enabling us to prototype multiple TEC forecasting models with hundreds of millions of parameters in parallel with the same code base. So to name the main three we've been focusing on, we've developed an Ioncast LSTM, a long short-term memory model, Ioncast SFNO, a spherical Fourier neural operator model, and Ioncast GNN, a graph neural network approach. In developing our models, we were inspired from previous works in weather modeling developed by our partners, namely Google DeepMind's GraphCast and NVIDIA's ForecastNet. And now I'll pass it off to Linnea to talk a bit about the results.
Thank you, Halil. So on the screen before you, you can see a comparison of the state-of-the-art empirical model, the International Reference Ionosphere, shown here on the left, with our ground truth JPLD maps shown on the right. And we present a quiet ionosphere event on the top, a moderate storm event in the middle, and a severe geomagnetic storm event on the bottom. And so these events can be used to evaluate our models. And we can see that Erie closely follows the Earth's magnetic field, but it fails to capture the non-hemispherically symmetric structure of the ionosphere that is present in the ground truth JPLD maps. And we can compare the performance of our baseline LSTM model trained on the data package that Halil mentioned against the Erie model and the ground truth. And the LSTM model forecasts over a 60-minute lead time, so it's looking an hour ahead. And we can see that it captures this asymmetric hemispheric structure of the ionosphere much better than Erie does. However, it is not quite a fair comparison because we take in very different input data to the Erie model, and the Erie model is not a forecast model. And we can compare the performance of this LSTM to our spherical FNO model inspired by NVIDIA's weather model ForecastNet, which captures the general motion of the ionosphere very well, but we can see that it fails to capture some of the smoothness that the LSTM model does. And finally, we can compare this against the performance of our graph-based model, Ioncast GNN, which is inspired by Google DeepMind's weather model GraphCast. And we can see that this model outperforms the LSTM and spherical FNO models by having a lower root mean squared error value, which is the white value listed on the bottom right of each plot. And we can see that it captures the general motion and asymmetries of the ionosphere very well. And while all of these models are performing very well at forecasting TEC over a 60-minute lead time, we are actively training and interested in improving our models to forecast over much longer horizons. So here on the screen before you, you can see the ground truth JPLD map on the left and the Ioncast GNN model on the right, predicting over a 12-hour forecast period. And we can see that it does quite well. And so we are really looking forward to seeing the next iteration of results produced by these models. Thank you, and I'll hand it off to Mike.
Thank you, Linnea. I invite you all to take a look at our work, just a quick peek. You can take a picture of this QR code, and I'll summarize our achievements during this sprint. We have curated a novel database that brought together diverse sources and structures of data. The data is machine learning ready and will be provided for the community to leverage and train their own models. We also built an operational catalog of NOAA solar events, categorized by both strength and duration. And we have completed building a machine learning framework that allows us to continue to evaluate various machine learning models, but also enables future researchers to leverage data sets, training and validation, as well as test infrastructure. Our Ioncast provides a novel ionospheric forecast model. And we were able to accelerate and expand our work by integrating data packages from Carmen and SDO, some past projects. And we are actively integrating our models with future projects and current projects like the Orchestrator project. Finally, as we see our models improve with more training, future work would look towards integration with NCAR operational models and other deployed models. So thank you for listening.